When it comes to programming, I am an adamant believer that even if you're programming in higher level languages like JavaScript or Python, that knowing the fundamentals of computer architecture and how CPUs work, so by knowing a lower level language like either C or assembly, you will be a better programmer because you know fundamentally underneath those abstractions how the computer has to be working. There's no other opportunity that your computer has but to behave in simple computer architecture ways. I get asked all the time when either I'm streaming or in the comments of these YouTube videos, how did you learn all this low level stuff? Like, what thing did you have to do to learn all this knowledge? And there wasn't any particular event or like singular place in my life where I learned all this stuff. I kind of picked up stuff in small little pieces along the way. And in this video, I want to show you guys one of the most efficient ways to learn low level stuff. Now, if you're new here, hi, my name is Ed. This channel is Low Level Learning, a place where I talk about computer security and software security. In my day job, I'm actually a security researcher. So if you're interested in that stuff or want to just hang out, hit that sub button. I really appreciate it. Now, one of the most efficient ways I think that you can spend your time when trying to learn either about security, about software security, or about just low level programming in general are these things called capture the flags. They are games where there are challenges put out that have hidden secrets inside of them, and you have to either take the binaries apart or exploit the software to get the secret out of the binary. So in this video, we're going to do a CTF challenge from PicoCTF, which is a well-known capture the flag. Let's get into it. So PicoCTF here at picoctf.org is actually a capture the flag platform put on by CMU, Carnegie Mellon University, the hosters of the Plaid Parliament of Pwning, one of the biggest, most well-known CTF teams in the community. But here we have PicoGym, which is a conglomeration of a bunch of different challenges that you can go right now for free, where there are challenges where you can learn a little bit about all of these different software and software security topics. When it comes to low-level programming, I think that these reverse engineering challenges are super effective because each one of these teaches you a little thing about assembly or a little thing about like the ARM architecture, for example. And by doing enough of these, you'll kind of begin to get this base of how computers work. And I think that will help set a good foundation for the rest of your programming knowledge as you go further into your career. Now, in honor of my new ARM course coming out, we're going to do the ARM Assembly 0 challenge. This challenge basically says they give you a chal.s, so this .s is an assembly file. It's a listing of ARM assembly. When you run the program with arguments this and that, what is the output? So what does a program print with these two arguments? In the flag format, the input we have to give to get our points is PicoCTF, and then this long string inside of the curly brackets. So let's go try it out and see what kind of trouble we can get into. So I've downloaded the file here. We have the chal.s file, and there's some kind of metadata up at the top. First, we can see that it's ARC ARM v8a, so that tells us that this is a 64-bit ARM assembly challenge. This was derived from chal.c, so this means that someone wrote the challenge in C, and instead of compiling the challenge down to actual machine code to run the program, they assembled it down to assembly, and then this is the output of that compilation step, right? This is .text, which means that this is the code that runs. So in programs, you have the data section, which is your readable and writable section of memory. And then on the other end, you have readable and executable memory, which is code, right? You can read it and you can execute it, but you can't write to it. Those are the kind of mutually exclusive two regions of memory in computing. Align to just means that we're aligning it to 2-byte offset, so we can't have code that starts at the value 3, because the ARM architecture can't execute outside of those boundaries, right? We have a global function 1. This is a function that gets exported. And here's the function 1 definition. So let's actually start from the main function and kind of walk through what's going on here. So if you're completely unfamiliar with ARM assembly or assembly in general, that's okay. We can teach you the basics of it right here, right now. So when you read assembly, the way that it operates is you have an instruction here that is the function or the action to be taken, and then the arguments to that action. So the very first line here we can read is store pair. So this is an instruction in ARM assembly that says, I'm going to store a pair of registers. Now, what is a register, you might ask? A register is just a piece of memory inside of the CPU that is named, right? So x29 is a register that refers to the frame pointer, so the bottom of your stack frame. And then x30 is the link register in ARM 32-bit or in ARM 64-bit assembly. The link register points to the instruction to be called or the instruction to be ran after the function returns, right? So this will be the place after the function that called main. So we're going to store the pair, we're going to store these two instructions at the stack pointer minus 48. So that's going to put those two into the stack frame. And all it's going to do is we're preserving these two registers because these are meant to be preserved across function calls, right? A lot of this is just setting up a basic stack frame. This is creating room for our main function to run. The real meat and potatoes of this function is going to be starting at this line here. And again, remember what the challenge is asking us. When we have the two arguments put into this program, this and this, what happens? Well, the question is then how do you access command line arguments when you're doing assembly or when you're even writing in C? Well, in C, you have this thing called argv. You have this thing called argv, right? Argv is the argument vector. It's a pointer to a list of pointers that have your arguments. So the first argument would be in address 1, and then the second argument would be in address 2. And obviously the first argument, the 0th argument, would be the name of the program. So what you can see here is we are pulling the argv value, which is going to live at x29 plus 32. We're going to load R, we're going to load the register x0 with that value. And then we're going to add the number 8 to that value. Now, what's magical about the number 8? Well, the number 8 is actually the width of a 64-bit pointer. So we are going from argv0, which is what it is right here, to argv1 by adding 1 to it. Now we're going to load that into x0, which is also a magical register, basically, that whenever you call a function, the first argument to that function lives in x0. Okay, cool. So we're going to call this other function a to I. BL means branch and link, which is the assembly variant of call, right? So a to I, we can go find that out right now. We can make a new window. We can do man a to I, and what this does is it converts a string to an integer. Okay, and that makes sense, right? Because again, we are going to take these numbers on the command line, they'll be put in via the keyboard, they're in ASCII, and then a to I is going to ASCII to integer those numbers so we can read them in our program as decimal values. Very cool. And the return value also comes out of the 0 register. So X is the 64-bit width of the 0 register, and W is the 32-bit width of the 0 register, right? So you'll see here in the man page, this returns an int. An int by default is 32 bits. So because of that, it comes out of the W0, and it's going to be stored temporarily in W19. And you can see here, we run this same operation a second time, only we don't add 8. What do we add? We add 16. Okay, what is important about 16? Well, 16 is 2 times 8. And what does 2 get us? The second argument. So all we're doing here is we're pulling out all the arguments from argv. We're a to I-ing them. We're ASCII to inting them. And then we're setting them up for this function call to func1. Now, I said previously, the 0 register is going to contain the first argument. Well, then what do you think the 1 register contains? The second argument, right? So what we're having here is func1 gets called with our first and second arguments from the command line, right? And that makes sense based on the prompt of the problem, but they are no longer in ASCII form, they're in integer form. Okay, so then we have to go and actually figure out what does func1 do? And whatever the output of func1 is, gets printed. Okay, let's go figure out what func1 does. Now, func1 is going to create some room on the stack. When you see a sub SP some number, the stack pointer is the top of our stack frame. So by subtracting 16 from that, we are actually making room to put memory inside of our stack frame. Every function needs an independent stack frame to run a function, right? So we are creating that stack frame here. Now we're storing W0 and W1 onto the stack, right? And you can see because we're saying store register 0 and store register 1 onto some location. So now when we're reading this code, we can know that the SP plus 12 is going to contain our argv1, and then SP plus 8 is going to contain argv2. Now what we're going to do is we're going to load into W1 the value SP12. Okay, so let's now say that just mentally we're taking notes here. W1 equals argv1. We could say that the same thing is happening in reverse. They've kind of flipped our arguments here. W0 is equal to argv2. Okay, and again, all we're doing here is we're doing basic math, some store operations, some load operations. Now here we have our very first kind of conditional operation, right? Because before we're doing everything very sequentially. Nothing is changing. Nothing is like happening out of order. The comparison operation is going to take 2 registers and it's going to set a bunch of flags in the CPU, and then the next operation will execute conditionally based on the outcome of this operation. So we're going to do some comparison. So we're going to compare argv1 to argv2, and then we're going to say if argv1 is less, because this is branch if less than, if argv1 is less than argv2, we're going to branch to the L2 label. And if the L2 label gets hit, we're going to load into W0 the value at SP8, which again is argv2, and then we're going to ret. So by putting it into W0, we're putting it into the return value of that function. So this effectively is return argv2. Otherwise, if this didn't run, we're going to load argv1 into here and then branch to L3 to return it. So this effectively returns argv1. Now, what's interesting is if you look at this and you start to kind of parse out the logic, if argv1 is less than argv2, return argv2. Otherwise, return argv1. Functionally, what does that feel like? Function 1 is actually just a max function. This will return the max of two values, right? How cool is that? That's pretty sweet. And then it'll print the maximum value because the return value comes out here, it puts it on the stack, and eventually it calls printf on that. So what we can do right now is we can actually assemble this program and then test it and see if we get the right operation. Now that's kind of cheating. I think what we should do first is just put the value into the format expected by the prompt and then use that to test our math. So we're gonna say that it prints the max of these two. This number is obviously larger and it wants it in this format. picoctf, quad x, no x0, but it wants 32 bits. Okay, so let's do the Python operation to do that. We'll do Python 3 and we'll do hex of this value. 1, 2, 3, 4, 5, 6, 7, 8. Very good. And we'll take this and we'll just say pico CTF. We'll say pico CTF of that value. Take this like this. Bada boom. And we solved it correctly again. I actually recorded this video previously, but I had the audio off the entire time. So you're getting the second recording of this video. So we got it right. That's pretty cool. So if you want to test this, you could just assemble this code, right? So you can go to downloads where I have the code. So you have to use a 64-bit compiler. So we'll do arm arc 64 GCC. We're going to output chow from chow.s. We have to do also static to make sure that it compiles correctly. So we can do chow. And if we don't give it two arguments, it'll crash. So we'll do chow 1, 2, and it always returns the max of the two values. So guys, I hope you learned something. I hope this was informative. I think like doing these CTF challenges is the most fun and easiest way to learn more low-level stuff. If you literally, if you just do one of these challenges a week for the next year, you'll come out on the other end, I think, just a much more knowledgeable, not only security person, but a programmer in general. So if you like this video, do me a favor, hit that like button, hit subscribe, and then go check out this other video about the PS4 that recently got hacked by a bug that is 20 years old. And it all came from stuff like this. Go check it out. We'll see you there.